Today I'm going to talk about fractured process. This is a joint work done with Professors Remzi and Andrea Arpaci-Dusseau. Processes are a major abstraction in modern operating systems. Processes provide programmers with a separate address space and a separate execution context. Because of this, processes have become a convenient abstraction for a lot of tools and techniques. So you have the Valgrind tool, which helps detect if a process has any memory leaks. You can apply various kinds of resource limits on a process. Restarting a process is still a very common fault tolerance technique, and so on. Modern applications usually use a few large processes. When they use multiple processes, it is usually for different threads of execution. They don't usually use multiple processes for executing different tasks that can be executed serially. But unfortunately, big processes are not a good fit for all these process-based tools and techniques that we already have. For example, let us consider an application that exposes a GUI interface and also has a problem that can be fixed by restarting one part of the application. Now, if the entire application is written as a single process, then restarting that process is going to also interfere with the GUI, and so it's not a very good mechanism to tolerate faults. Similarly, if the process is really big, restarting might also take a long amount of time. Also, if you are going to apply a tool like Valgrind to the entire big process, the overhead of the tool is probably going to be too high for it to be useful in practice. So there are ways to fix this. You could maybe design your application as consisting of multiple small processes that interact with each other. The disadvantage with this approach is that the overhead is going to be too high because interacting between processes is costly. People have also come up with many other abstractions that allow you to do some amount of isolation, some amount of restarting, and so on. But none of these abstractions offer as general techniques as process. So our solution is to bring back multiple small processes interacting via RPC in a single machine. But instead of saying that an application always maps to one static set of small processes, we are saying that if you have a problem with one part of the application, then only then isolate that part into a separate process. And we can also do this isolation in such a way that it interacts the isolated part interacts with the rest of the application in a really small way. And we are also targeting existing C applications. So we do require programmers to change a bit of code to use our framework where you can isolate small parts of the application into separate processes as and when needed. But we try to keep that amount of annotations that the programmer has to do small. And also, instead of saying that we are only providing isolation, we also want to provide a few more things such as restarting that are possible with processes usually. So this is going to be the outline of the rest of my talk. I'll first give an example of how putting different parts of the application into separate processes can actually be useful in the real world. Then I'll be talking about the exact benefits that our framework offers and what you have to do to get those benefits. I'll be talking a bit about the programming annotations that a programmer has to do and the implementation. And finally, I'll be talking about how efficient our framework is in the real world. So the example. For example, I'm going to use the Pidgin application. It's an instant messaging application. It has a graphical user interface. It is a fairly complex piece of code. It has about 300,000 lines of code. We are looking at 4 bugs that have already been patched in Pidgin. They have already been patched in, I think, 2011. We are specifically looking at 2 memory leaks and 2 buffer overflows. And I'm going to explain how the fracture framework could have helped solve these 2 bugs easily. So first, with the memory leaks, so the usual technique to prevent memory leaks is that a programmer writes a piece of code and then before shipping it to the users, runs it on top of a memory leak testing tool with some workloads. And if there are any memory leaks, then that tool is going to find and report to the programmer, and the programmer is going to fix it. Now, the memory leaks in Pidgin, they occur only in very specific workloads that would probably never be tested in the developer's environment. So the only way to have found these memory leaks would have been to actually ship the code with the Valgrind tool enabled on the code. But unfortunately, that has too much overhead, and so you cannot, essentially, the memory leaks in Pidgin cannot be found without inconveniencing the users a lot. So with Fracture, what you can do is, in each of the consumer's place, you can split a part of the Pidgin, a very small part of the Pidgin separately, and you can apply Valgrind to only that part. Then you can send back all these reports that Valgrind produces in the different consumers' places to the developer, and you can aggregate them, and then you can use that to fix memory leaks. And in each user, in each consumer's place, the overhead of running Valgrind is going to be small because Valgrind is applied only on top of one small part of the entire application. Now, the second kind of bugs that I'm going to show as an example is buffer overflows. So these buffer overflows, again, happen on only very rare workloads. Now, there are already many techniques to tolerate buffer overflows. So RX, a paper that came out in SOSP 2005, has a very nice technique. What RX does is, it whenever it sees a crash, it restarts. It doesn't know the cause of the crash, so it's going to restart the process, the application, with different environments applied to the application. Each of these environments is designed to tolerate one particular type of bug. So when the particular environment that is designed to tolerate buffer overflows gets applied, then the application will continue running without crashing. However, if you are going to apply the same technique as RX here, since Pidgin is a GUI application, each time you crash and restart, that will be visible to the user and it will interrupt the user's flow. With Fracture, what you can do is, the first time you see a crash, the next time when you start, you just isolate the GUI part of Pidgin separately. And for the rest of the application, you can keep applying the RX-like idea. You can also go a bit further than that. You can say the rest of the application, I know that some part of it has a problem, so I'm going to, each time I restart in RX-like mechanism, I'm going to do a binary search. I'm going to split it further until I find that exact spot where the problem is. And then I also can isolate that exact part from the GUI in the most optimal manner possible. Okay, so the example almost talks about Fracture like an evangelical framework. So I'm going to now tell you about the exact benefits that Fracture offers and what you need to do to get those benefits. The first benefit is isolation. So to achieve isolation, we start with the programmer first dividing the entire program into modules. Now, I'll be explaining more later, but for now, modules are just any collection of functions. So if a program looks like this, then the programmer can say, I'm going to divide it into two modules, module foobar and module scram. After this, at runtime, during each run, the user can specify a runtime configuration which essentially says how many processes should the application be divided into for this run, and which modules should be contained in each of those processes. So you essentially distribute those modules into processes, and you can change the distribution for each run. We call each of these processes as a fractured mini process, just to distinguish it from the actual process abstraction. So here I have shown an example runtime configuration where you split the application into two FMPs, into two processes. FMP1 and FMP2. FMP1 has one module and FMP2 has the other modules of the application put into it. The user can also say for run FMP1 with valgrind or with some memory limits. We call each of these, valgrind or memory limits as the environment of the FMP, so it's going to be called an FMPE. Now, what are the different runtime configurations that an user will normally use? One thing that the user can do is put all the modules into a single process, and this would hopefully provide the same performance as you will get if you run the application without fracture. And this is the normal mode in which we believe most applications should be run in. The other kind of runtime configuration that you can do is put each module in its own process. Now, this is going to give you a very high isolation, but it will also be but it will also cost you a lot and it will be very inefficient, and we don't think this kind of isolation should be usually used at all. Now, here is the actual useful kind of runtime configurations that you get with fracture. You can put a suspicious module alone in a separate process, and that's going to give you hopefully a fair amount of performance. Or you can say, I want to isolate this particular module from the rest, or this particular module from another important module, and you can ask fracture, what is the most efficient way in which I can distribute modules among two processes so that the overhead is low, but the suspicious module is isolated from the important module. So that we call as intelligent partitioning. So yeah, those are the benefits of isolation that fracture provides, and how you use isolation. Next, about restarts, replication and sampling, which is another set of benefits that fracture provides. I'll be explaining what exactly I mean by replication and sampling in a minute. But again, we start with the programmer. The programmer has to mark each module with its capabilities. So a module can be capable of being restarted, of being replicated, or being sampled, and the programmer has to mark what each module is capable of. Once the programmer marks that, then for capable FMPs, the user can say restart this FMP if there is a crash, or replicate this FMP twice. So what exactly are restarts? To explain this, we want to first imagine each FMP as a microserver which receives requests from the other FMPs and gives responses. When you imagine it as a microserver, when I say restart, it means that the FMP will be restarted with the most, if there is a crash, the FMP will be restarted with the most recent request. Now, why would you use restarts? And the important point to note here is if an FMP restarts, it is totally transparent to the other FMPs and the other modules. The use cases, like I already explained for Pigeon, this is going to be one, you can restart one module without affecting GUI or another piece of important module, and it's going to be faster than restarting the entire application. And also, you can change the environment of the restarted part with each restart, so you can apply things like RX or software rejuvenation. Okay. The next is replication. By replication, I mean that for a single FMP, you can actually have two processes that does which both receive the request and which both reply. The reason you would use this is if you have two slightly differing versions of code. Say you applied a patch, and so you would separate out all the modules that that patch applies, and you would put them in a separate FMP, and you would actually replicate them. And one instance of that FMP, just to say one actual process can run the old code, the other process can run the new code, and you can find out whether they behave the same way or not. The third one is sampling. Here again, for each FMP, you actually have multiple processes. But instead of replicating, instead of sending all requests to both processes and getting back responses from both processes, you send each request you send to either of those processes. The reason if you do this is, say you have isolated one part of the application and you have applied Valgrind on top of it or some tool on top of it, and it is still too slow. So then what you can do is you can actually sample that isolated part into two different parts, and you can apply Valgrind only on the part that is less used, reducing the overhead further. Okay, so those are the benefits. Of course, the fracture framework is not magical. You still have to change the code for making all of this work. So I'll be describing what those program annotations are. So essentially, you can put any, not essentially, but sorry. You can put any set of functions into a separate module with some restrictions. You cannot have global variables across modules, and you cannot have access OS resources across modules. And there are some special semantics associated with pointer parameters and heap allocations. I'll be describing them next. So with pointer parameters, when two modules get put into two separate FMPs, anything that is referred to by a pointer parameter, we serialize it and we send it across to the other FMP. And when there is a reply, we bring it back. We deserialize it, essentially. For this serialization and deserialization to work, fracture, in some cases, say you have a pointer that actually refers to an array. In cases like that, you would have to annotate the program and say this pointer actually refers to an array. With respect to heap allocations, disallowing pointer parameters, disallowing like actual by reference pointer parameters and global variables has one effect, which is to say that two modules cannot point to the same piece of data. So each piece of data has to have its own, logically has to have its own owner module, and so only one module is allowed to point to that. For labeling module capabilities, again, we ask the programmers to imagine each module as a separate server. And if the actions of the server are deterministic and idempotent, then you can mark the module as being capable of restarting replication and sampling. Now, if the module is not deterministic and not idempotent, then there are a few more complex tests that you can conduct to find out whether the module is actually possess any one of those three capabilities. Okay, so how does this all work? For interaction between processes, we use shared memory queues. It's just, you can say it's just another implementation of RPC in the same machine. For doing things like restarts, replication, and logging, we essentially, for restarts, we log all the queue entries that go to a particular process, and when a restart has to be performed, we replay from the log. For replication, we mirror the queue in two different processes, and we collate them back when the queues are dequeued. For sampling, we multiplex and demultiplex into two different queues. The intelligent partitioning that I talked about, where you could ask fracture, if I want to separate module A from module B, what is the most efficient way to separate it? The way that works is fracture records the workload being performed by the user, and it finds out the amount of interaction that is occurring between different modules. And from this data, you can use a min-cut algorithm, a graph min-cut algorithm, to find the most efficient way to partition such that A and B are divided. So evaluation, of course, it was not, we evaluate with 4 real-world applications. One is a web server that is both CGA capable and multi-threaded. 2 are Fuse, that is to say file system and user space file system implementations. And of course, we are with Pigeon. Now, there are multiple ways for dividing an application into modules, and we use a different strategy for each of these. For null HTTPD, for example, we try to put each function into a separate module. For SSHFS, we look for logical divisions within the code, and we put each logical division into a separate module. Now, of course, programming, annotating, modifying the program wasn't too easy. It is really hard to quantify how much programming effort we put in, but to annotate pointer parameters so that serialization and deserialization can happen, we had to do annotations for 57 pointer parameters in total. To put that number into context, we had a total of 104 modules across the 4 applications. The most difficult part about modifying the code to make it work on top of Fracture was to find those data that were being heap allocated and to verify whether they were actually being shared between 2 modules or not. And we also found that if we are trying to divide an application according to logical divisions that are already present in the code, for example, like we did for SSHFS, it was easy to do that, as opposed to if we want to impose a particular division ourselves, then it is going to be much harder. Next, I'll be talking about the actual performance we get. So I'm going to show each of the applications in the x-axis. The y-axis is the performance of the application normalized to the unmodified version of the application run in a normal machine without using Fracture. So when you use Fracture after modifying the application, if you ask Fracture to put, if you use a runtime configuration and tell Fracture to put all the modules in a single process, this is the performance that you get. It's almost the same as running the application without Fracture at all, which is good news. Now, if you ask Fracture to put each module into a separate process, then the performance gets affected a lot. So again, we don't think this should be used in any of the applications, except maybe for SSHFS, which seems to give good performance even if you put each module into a separate process. Now, of course, if you want to isolate one module away from the rest of the application, the performance differs based on the module that you're trying to isolate. And here I have tried to show the distribution of how much performance overhead is there by using box plots. So if you are able to see the median line of each box plot, it seems that isolating about 50% of the modules seems to have only a tolerable overhead. However, there are a few modules that are that it is really hard to isolate from the rest of the application. Now, we measured performance for restarting different modules or replicating different modules or sampling different modules. The performance is almost the same as you would expect when you isolate the module. So if you want to restart a particular module and you put that into a separate process, you get essentially the same performance as separating out that process just for isolation. So in conclusion, we are trying to say that an entire ecosystem of tools and techniques is all built around the existing process abstraction. And unfortunately, a lot of those tools and techniques seem not useful now because applications want more performance and they put a lot of different things together in a single process. We believe that redesigning RPC with some additional thought can help you use those tools and techniques even in the context of modern applications. So yeah, thank you.
So I have a question.
Yeah.
That part of the system that helps you to cut, to find the best cut.
Yeah.
Does it also help you with actually finding, it seems like what really the conditions for isolation are similar to encapsulation. You're really kind of trying to figure out when the module is encapsulated and they don't share data.
Yeah, yeah.
So are you helping in any way? Because you're saying, I'm helping you to find the best cut? Does the programmer has to specify
Right.
for each such cut?
No, the programmer does not have to specify for each cut what is the interaction. That will be calculated automatically. The programmer does have to specify all the ways in which you can divide it, right? So that's when you specify the modules.
And those division ways have to satisfy your conditions, right?
Yes.
In terms of not sharing.
Yes, yes.
So that's
That's
quite a.
yeah, but we have found, so of course the programming overhead differs a lot between different kinds of applications, but there seem to be a certain set of applications where there are very obvious logical divisions where the only reason they put together these things is because they don't want additional overhead. So yeah, that's what we found.
Thank you. Any other questions? Yes.
Hi.
Oh, mine doesn't work.
That's
So from your talk, I kind of have a feeling that the restarting is stateless. Do you also maintain the state of the components of the modules you're restarting? And if so, what's the overhead of maintaining the state?
So we don't. So the state that we don't maintain like internal state of the application. What we do maintain is if you received a request, if an FMP, if a process receives a request and it interacts a bunch of times with other process and then it crashes, right? We will be maintaining all the state from the point where the request came in to the point where the crash occurred, all the interactions between the process. And that does have some memory cost. And I have not seen a case where that actually affects performance. But it is possible that, memory is used more.
And preserving just this part of the state, does it also affect correctness of execution? That you just restart what you have
So
in
yeah,
state where you actually crashed?
Yes. So again, the programmer has to make sure that so when the programmer labels capabilities, labels that a module can be restarted, the programmer has to make sure that only with the state the module can be restarted.
Okay, thank you.
Yeah, so I've started to attend eCoop and OOPSLA kinds of conferences. I was curious to know what the pros and cons. I mean, after all, some of the applications you're talking about are probably programmed in Java or a language of that type, and they're very powerful tools now.
Yeah.
For
So if you that's very correct. In fact, with Java, I have I haven't exploded, but I feel that all these can even be done automatically. The divisions can even be done automatically. What we are concentrating on is C programs. And for C, as far as I know, the
you don't have to
tools,
convince me.
Yeah.
So, right. Okay.